So, welcome to this particular lecture. Now, in the last lecture, if you remember, we basically solved the two scaling extremes and we showed that what are the relevant numbers, non-dimensional numbers, as well as what are the corresponding boundary layer thicknesses. Mainly it was delta t, delta and delta v. These were the three types of length scales that we actually derived. Now, to compile all of them, okay, you can look at table 4.1 of Adrian Bejan. Okay. So, here you can see that when the Prandtl number is greater than 1, okay, the thermal boundary layer thickness, which is your delta t, is basically h into Rayleigh number to the power of minus 1/4, right, the standard. When Prandtl number is less than 1, you just add the Prandtl number to the power of minus 1/4 factor, right. This is already what we did. So, this is a compilation. So, this is basically your delta t, right. Then, okay, there are three things regarding the corresponding velocity scale that is introduced, okay, the corresponding wall jet thickness as well as the distance from the wall to the velocity peak, right, three parameters which are important. So, the velocity scales are very straightforward, they are always introduced by the delta t. Remember one thing, even if you forget everything else, right, it is the delta t, right, it is a buoyancy term which basically introduces whatever is the relevant velocity scale, right. So, that is what it is, right. It is always the buoyancy term regardless of whether you are mapping it with inertia or with friction. That is what we have done in the two cases, right. It is always determined by the buoyancy term, right. Okay. So, the velocity scales comes out to be like this, these two marks that we said. So, this is V, right. Okay. Now, the distance thickness of the wall jet is basically the thickness of the delta, that means whatever is the delta, that is delta V or delta that you are dealing with, that is what it is, right. Okay. So, that is what it is. So, that has been kind of put forward over here, okay, and the distance from the wall to the velocity peak, that means where the velocity peak will kind of happen, that is given by these two terms over here, right. So, all you can see all are h into RAH to the power of minus 1/4, right. So, basically if you talk in terms of cloning, these are all cloned kind of quantities, right, with a stretching factor appropriately added, okay, depending on the situation of the problem. Because ideally if your Prandtl number is equal to 1, all of this thing just vanishes, right. You get what we call a royal, I mean everything is the same, there is no limits obviously, it is just that Prandtl number is equal to 1, right. So, it is just because this takes into account the differential diffusivity and the difference between momentum diffusivity and the thermal diffusivity into the picture. That is all that it has done, right. The Prandtl number is a quantity which essentially takes care of that, right, momentum diffusivity versus the thermal diffusivity. It is because of that we need these stretching factors, okay, we need these stretching factors essentially because of that, right. Of course, these are at the two extremes that we have pointed things out, right. And as I said earlier, there are three numbers BOH and GRH, right. Okay. So, where BOH is basically RAH into Prandtl, this is basically RAH divided by Prandtl, right. Okay. So, these are the factors, okay, that are responsible, okay, these are the three most important quantities. Look at their applicability. So, next time when you look at a problem, okay, look at the applicability, that which number is the most important one, okay. It is not just Rayleigh, it depends on what problem you are actually dealing with, okay. For example, in liquid metals, Grashof number will be very important, okay, and things like that. But normally in the case of our natural convection problems, okay, you know what we do, we basically use this interchangeably. Okay, we use Grashof, Rayleigh and all these things in a very mixed match kind of a fashion. Okay, we do not partition it like this. Sometimes it may be very difficult to partition it in the first place. Okay, but normally as you can see, these numbers are all pretty much close to each other with a Prandtl number factor added, okay, here and there, right. So, in essence, okay, they designate the basically the scales of the problem. Okay, that means what are the different scales that are actually responsible for each of the problem. Okay. So, of course, you can see that why your another thing to note in normal natural circulation problems, you will find that usually this Rayleigh number and Grashof number values are very high. and you will find 10 to the power of 4, 10 to the power of 5 and things like that. That is a very normal practice even before you move on to the turbulent regime. Okay. The reason because is that everything is scaled as 1/4, right. So, everything is kind of, there is a factor of scaling that is always inbuilt into the system. So, it is not just the Rayleigh number per se, it is the 1/4 of the Rayleigh number that actually matters. Okay. So, these are some of the subtle things that you should kind of remember, okay, and these are the things that can come in handy, that it is very different from the natural convection, from the forced convection problem. Okay. So, let us look at the length scales put in a kind of a formal graph, okay, over here. Okay. So, what we have done is that basically what Professor Adrian Bejan has done is basically you have divided by the length scales divided by this factor h into Rayleigh number to the power of minus 1/4, because that we saw was universal regardless, right, wherever you put it is the same. So, it is kind of a regime map per se, this plotted with Prandtl number, right, and here you can map out the different quantities, correct. Okay. So, for example, when your Prandtl number is less than 1, okay, you have the Prandtl number to the power of minus 1/4 graph, right. You have that particular line of graph which basically gives you a delta t, right. So, you can basically map out that you now belong to this family, it is like a family tree. So, you belong to this particular family, right. Okay. Similarly, okay, you can map out for Prandtl number greater than 1, right, you can map out that what will be this, right, what will be the value of your delta, that kind of a thing. Okay. And similar thing goes, and you can see that here it becomes flat, right. That means when for Prandtl number 1 up to about 100, okay, you will find that this particular delta t is of the order 1, okay, is of the order 1. Why that particular thing happens? It is Prandtl number greater than 1 situation. So, remember that delta t in that particular case is independent of Prandtl number. You remember that it is h RAH to the power of minus 1/4. So, naturally this value will be 1. Okay. So, 1 and beyond is basically independent of Prandtl number, correct. So, that is why you get your delta t. However, the velocity boundary layer is not the same way, right. So, for Prandtl number greater than 1, you have this particular kind of a dependence, Prandtl number to the power of half dependence on your velocity, right. That will be evident if you guys get confused, is basically if you look at this particular thing, which is the basically the thickness of the wall jet, it will be very apparent. It is Prandtl number half factor is there, right. Here that factor is not present, all right. So, this is the delta t, this is your delta or delta v, whatever you call it. So, this has got a Prandtl number half, this has got no Prandtl number. Now, if you go and look at this particular these two lines of the plot, you will find here it is 1 flat, because there is no Prandtl number, no matter what is the Prandtl number value, it is of the order 1, right. Here of course, the velocity shows that Prandtl number half dependence. So, with Prandtl number that will go up, okay, which is logical also. As you increase the Prandtl number, your velocity will be is going to be felt at larger and larger distances into the reservoir, right. Now, let us look at the other situation, right, which is the second one. In that particular case, you see it is a Prandtl number minus 1/4, right. The thickness of the wall jet is very small, right, and this is the corresponding Prandtl number value on the other side, right. So, if you look at then this particular plot and this particular plot, you will get the meaning, right. Both actually has got that Prandtl number dependence right now, right, okay, and your velocity boundary layer is different from your temperature boundary layer, right, and this is obviously going to be smaller than that. So, as you go on decreasing the Prandtl number, right, okay, your velocity boundary layer becomes thinner and thinner and thinner, okay, which is kind of obvious because you are, I mean, restricting it very closer and closer to the wall, right. Whereas, in the other case you will see the reverse trend that will start to happen, right. So, you can see there are basically a family of 4 curves that you can see, 4 families, right, with Prandtl number equal to 1 is being the point, the focal point where everything kind of falls, okay, right on the money, right. So, there is absolutely, it's basically as if you are kind of diverging from that particular point as you go in either directions, Prandtl number greater than 1 or Prandtl number less than 1, clear. Okay. So, based on this, okay, now let us look at the, so far we have done a lot of scaling. So, now it is the right time to do a little bit of math, okay, which is basically we will shift to the integral analysis. Okay. So, integral analysis, and by now you are most familiar with what integral analysis is, right. So, I will write the y momentum equation, because that is the only equation that is kind of is important. Right. Okay. Continuity. Right. Okay. Energy. These things are kind of very common. Okay. So, now what is the tradition to do in an integral analysis? You basically integrate out one of the dimensions, right. In this particular dimension it is a x dimension. Previously it was a y dimension, but now your plate is actually rotated. Okay. So, your x points out away perpendicular to the plate. So, naturally you are going to do the x dimension x integration first, that means integrate out with respect to x. Okay. So, integrating with x, where x is greater than delta or delta t, right. That means it is greater than both actually, right, and we apply this to the y momentum equation first. So, what will happen? I am not going over the Leibniz and other kind of rules. So, you can read about it once you consult your forced convection notes. Got it? Okay. So, now getting rid of a few terms. Okay. Why is the first term disappearing? That is because of the simple reason at the wall, okay, and at x, right, u should be at actually equal to 0, right, because we have taken x which is beyond all of this limit, okay, and v also should be equal to 0, right. At the wall of course u and v both are equal to 0, okay, and the far field of course you have v to be equal to 0, right. So, anyway the first term goes away because of that particular reason, second term stays, and you have this particular term. Now, here of course, we are evaluating at x equal to 0, but because at x equal to x, which is far away from the wall, you naturally would not have any shear stress coming into the picture, because it is a quiescent fluid, right. Okay, there is no provision of having any shear, right. Okay. So, this is the y momentum equation, right. Similarly, let us look at the energy equation now. Okay. This is the energy equation. You once again integrate with respect to x, right. You integrate with respect to x. So, you get ut is 0 to x. It is a little bit boring, but I mean this is a necessary thing that we have to do. Okay. it is equal to 0. So, that is once again the same logic. Okay. Far field you do not have a temperature gradient anymore, okay, at x equal to x. So, here of course, the situation is at x t infinity, okay, and d by dy, okay, integrated from 0 to x v t dx minus alpha dt by dx evaluated at x equal to 0, right. If you substitute this particular guy from the continuity thing, okay, at any x that you are actually evaluating it, okay. So, you get using continuity, okay, you get minus d by dy 0 to x v t infinity dx plus d by y. Okay, or in other words d by dy 0 to x v t infinity minus t dx minus dt by dx x equal to 0, right. Okay. So, that is what you get. Now, what is the next step that you usually do in such cases? You basically choose a profile for temperature and velocity, right. And you already got a feel that these profiles looks very exponential-ish to you, right. Velocity, for example, goes up and then it comes down, okay. So, it should have a multiplicative effect somehow, right. If you, when you choose the temperature profile or the velocity profile, you should have that thing in mind. Temperature profile is kind of shows that monotonic kind of decay, right, the delta t from a delta t perspective. So, let us say if the Prandtl number is much greater than 1, okay, that is one of the limit, t minus t infinity, if I write it like this, x by delta t, will this be reasonable? I think it would be reasonable because it shows that exponential decay, right, of the quantity, and it looks pretty exponential decay, right, when we actually did the scaling, right. Okay. But velocity is a little bit different, it is a little bit of a different beast than that, right. So, for Prandtl number much greater than 1, okay, the temperature profile is given by this. I think we can buy into this particular argument, whereas the velocity profile, as I said, velocity is a 2 parameter model, right. So, you can have something like that, right. Okay. So, it is 1 minus that, okay, and it is exponential of x to the power x by delta. Okay. So, it is like a 2 parameter model that we are proposing over here, right. In addition, we define one more quantity which is q, which is delta by delta t, which is, as we have proved by now, it is a function of Prandtl number of some sort, right. So, what will happen? Now, you substitute these two things into those two equations, momentum and energy, right, okay, and from the momentum you are going to get so from momentum this math you can do. Okay, the energy equation right. However, there is one small catch over here, right. The catch is that what are the unknowns in this particular equation? In this particular equation that we have done, okay, there is a delta which is of course an unknown, there is q which is of course an unknown because we do not know what function of it is in terms of Prandtl number, and then there is of course that v, the maximum velocity, right. We know the delta t, we do not know what is the velocity that is going to be incorporated, right. So, based on these, okay, we need a third equation. Okay, this equations has got 3 unknowns, 2 equations, ill-posed problem, you cannot solve it, right. So, you essentially need one more parameter over here, right, one more equation, and that equation is usually derived, the third equation, let us call that the third equation. Okay. So, once again very close to the wall, this is the same logic that we did earlier, okay, very close to the wall, inertia is negligible. Okay. So, it is basically friction that is balancing the buoyancy, right. Okay. So, you have g beta T naught minus T infinity is given by gamma, right, that is the equation, right. So, simplifying, if you now once again back substitute the same thing, 5 by 6 q square q plus half and q plus 2 equal to Prandtl number, okay, the third equation. Okay. So, basically now what you are going to do, you are going to solve all these 3 equations in a coupled manner, right, and basically find out what is the solution. Not very trivial, it requires about 2 classes to work it out, okay, to work out the full thing, okay. But I mean you can do the solution as a practice, but the whole point of this is not to solve the equation, but basically to show that delta by delta t is given by 6 by 5 Prandtl number to the power of half, which agrees with the scaling argument that we formulated earlier, right. We said it is going to be Prandtl number to the power of half. So, 6 by 5 is just a factor that sits in front. Nusselt number is given by 3 by 8 q cube divided by 1 plus q, q plus half and 2 plus q, that is the Nusselt number raised to the power of 1/4 Rayleigh number to the power of 1/4, right. This is q, this is not gamma. Okay. Now, for Prandtl number as it goes to infinity, because it is a high Prandtl number fluid situation, the Nusselt number basically becomes 0.783 Rayleigh number to the power of 1/4, which almost agrees with the order that we calculated earlier. We said it is going to be Rayleigh number to the power of 1/4, and in the limiting case of Prandtl number going to infinity, it comes out to be about 0.8 of Rayleigh number to the power of 1/4, right. So, this is an extraordinarily powerful thing that we did in the scaling. We provided the correct scaling, and that is validated over here, okay, including the ratio of the 2 boundary layers, right. So, this is the most generic form for any Prandtl number. This is the form in the limiting case when Prandtl number goes to infinity. Okay. So, for the low Prandtl number, that is Prandtl number much less than 1, you have your view v is x by delta t 1 minus exponential x by, that is the v profile once again. Look that we have changed it a little bit, the inside has changed now to delta v, previously it was delta t, that is because the peak is now appearing within this, previously it was appearing within the delta t, now it is appearing within delta v. Okay. So, it takes into account the correct estimation. And what about the temperature? The temperature profile should remain the same, right. There is no reason to change the temperature profile because it is still delta t, whether delta t is big or small, that does not matter, right. Okay. So, what we do is that once again you solve as before, right. So, you get your Nusselt number to be 3 by 8 to the power of 1/4 q1 2 q1 plus 1 half Rayleigh number to the power of 1/4, where q1 is delta v by delta t, right. In the limiting case, when Prandtl number goes to 0, almost close to 0, this becomes 0.689 into Rayleigh number y into Prandtl number to the power of 1/4. Once again the scaling works, that is because we are getting a number which is of the order 1, correct, right. Okay. So, this particular thing, if you look at this particular problem now, okay, you will see that we have established this is the most generic for any Prandtl number. Of course, given that Prandtl number is much less than 1, not for any. This velocity profile is very important, takes into account the correct form. Correct form is very important, because when I said earlier that you need a velocity profile which is, remember in your flat plate boundary layer we said, okay, if you recall the situation, that this is your boundary layer profile, right? You have to match a few boundary conditions. So, what prevents us from having this? You can have that, right? Or what prevents us from having this? So long as you match the gradients somehow, right, and match the boundary conditions, you are good. But these profiles are not correct, because they do not have the correct form. Okay, form is very important, because you cannot have kings and other things appearing in the velocity boundary layer profile, okay, which is unrealistic. What will lead to that? There is no physics. Okay. So, similarly here the correct form is very important. Velocity should go up and then it should come down. It should not show a multimodal peak, for example. You might argue, why not a multimodal peak? What is the, why there should be a multimodal peak in the first place? Okay. What actually generates a multimodal peak? We are assuring that at two ends the velocity should be 0. So, there it must have a peak somewhere, right. That peak in a certain case is within that delta v, that peak in some other case is within delta t, right, because in that case delta is more than your delta v, and the peak cannot be actually in the delta region which is beyond delta t, because there is no driver. So, why should the peak actually shoot up there, right? It should shoot up within delta t and it should decay within delta, right. Similarly, in the other case, because the driver is still delta t, the peak happens within that small layer of delta v, because your momentum diffusivity, it is a low Prandtl number fluid situation, right. So, the momentum is more arrested or in that particular region, right. So, based on these two conditions, okay, the correct velocity profile descriptions are given by that. Okay, though this is kind of not exact, because we have taken exponential, it could be other functions which is similar to that, and you can also show that if you use other functions you will get very similar results as well. Okay. So, it is not like that your this number, this 0.689, this might change a little bit. Of course, we will do in the next class the similarity solution, and we will try to show through the similarity solution that what is the exact values of these particular profiles, okay, and how these profiles actually evolve, because this is still done through the integral arguments. Okay. So, see you in the next class, where we will start the similarity solutions, okay, for this, and try to see that how the profiles look like. Thank you.